and welcome to the lecture 3 of module 2. In today's lecture, we are going to talk about the emerging trends at the distribution level grids and how these emerging trends are leading to big data analytics. So, in today's presentation, we will start our discussion starting from the evolution of power systems and then what are the present day distribution systems look like. Next, we will talk about the active distribution networks in detail, following the key characteristics of the distribution level signals in present era. Then we will talk about the research challenges which are emerging because of these latest trends which are occurring in active distribution networks. And finally, we will talk about the need for big data analytics. So if we start our discussion from this very generic picture of a conventional power system, then you can see that we have the basic generating stations which usually generate at the level of, let's say, maximum of 32 kV. Now since these powers are to be transferred over a long distance, so there is a need to step these voltage levels up to extra high voltage levels or high voltage levels, which means they are to be stepped up to, let's say, 440 kV and above. Finally, we have a sub-transmission level network where we step down the voltage and thereafter we can tap the power from this level and give it to some industrial users. From there on, we have our distribution network finally, and this is where we are, that is the end users or consumers which are residential in nature. So we have the voltage level of 440 volt or 230 volts. So this is the conventional electric power system. So as far as its category is concerned, we can categorize the whole of this conventional power system mainly in generation level, transmission level, sub-transmission level and the distribution level. Now conventionally, these three levels, that is generation, transmission and sub-transmission network level, they are managed and operated by the entity which is known as transmission system operator, that is TSO. Now this TSO, he gets the data from this entire three levels of power system, that is generation, transmission and sub-transmission, and from the gathered data and based on the targeted applications and its output, he will decide and take some corrective or preventive actions. Now as far as this monitoring is concerned, conventionally in the traditional power system, this role or this duty is done with the help of SCADA systems, where SCADA stands for supervisory control and data acquisition. Now the very main entity of this SCADA is what is known as remote terminal unit, that is RTU. Now this RTU, they are dispersed along this power transmission grid and they capture the data from the CTs and PTs which are installed throughout the transmission grid, where the CTs and PTs are nothing but current transformers and potential transformers. So what these CTs and PTs do? They will capture the voltage and current signals and they will give the RMS values of these analog quantities to the RTU, and RTU further communicates it to the control center, where this TSO is sitting, that is the transmission system operator is sitting and having a system-wide view. Now this traditional SCADA system has been working well until recently, and the major shift in the monitoring and protection and control of the power system, this whole system or this whole scenario got changed soon after the US blackout in 2003. Now as most of us know that in 2003 the US faced one of the major blackouts in the history, where almost northern east part of the United States and the central part of the Canadian grid they got blackout. And the blackout was so severe that it took almost a week to completely restore the system. Now, when a post-mortem analysis was done, it was found that at heart the main reason behind that US blackout was the lack in real-time monitoring of the power system. Therefore, a need was felt for the real-time monitoring and subsequently for the real-time protection and control of the power system. So, to achieve this target, a new measuring device came into being, and that is popularly known as PMU. And the full form for PMU, as most of us know, it is Phasor Measurement Unit. Now, what this phasor measurement unit does, it again captures the analog data from again the CTs and PTs, and it processes it, and it gives the phasor information of those analog quantities, whether it is voltage or it is current. Now, as we can see in this slide, that these PMUs are dispersed along the grid. So, they will be placed at various substations at various voltage levels. And we can also see that this GPS satellite or this satellite signal plays a very crucial role in this PMU device. And this whole thing combined together is now known as, popularly known as WAM system, where WAM stands for Wide Area Monitoring System. So, WAMS, that is WAM system. So, basically the traditional SCADA system has now been at most of the places slowly getting replaced with what is now known as WAM system, Wide Area Monitoring System. Now, what happens here is that because these PMUs are geographically dispersed along the power grid, this GPS signal is providing them a common reference for their sampling. So, what happens that although these various measuring devices could be geographically far apart from each other, but when they send their measurements to a control center or to a central location, which in this case is known as PDC, that is Phasor Data Concentrator, then there, along with their phasor measurements, they also have a time tag associated to that. Now, based on the time tag, accordingly we can get to know when a particular measurement was taken by that PMU, and accordingly the now transmission system operator can take a better informative action or preventive action as achieved from these PMU devices. Now, soon after this 2003, in most of the utilities, they have adopted this WAM system. But in Indian context, in India, the need for this WAMS technology was felt soon after the Indian 2012 blackout. Again, as we most of us know, that in July 2012, our Indian grid, it also faced one of the largest blackout in the history. So again, under this blackout, what we had, our northern and eastern part of India, it got affected, and for 2 days the power supply was interrupted. Of course, later on the grid was restored, but when the post-mortem analysis was done, what was the cause behind this massive blackout, so again it was found that one of the line was overloaded, one of the major corridor in UP, they were overloaded, and system operator could not assess that situation, and they were not told in real time status of the power system. So, had there been a real time monitoring in the system in Indian grid, we could have avoided that blackout. So, after 2012, this WAMS technology is also picking up in Indian grid as well. So, under one of the power grid major projects, India is undertaking to deploy a massive amount of these sensors, these measuring devices known as PMUs, somewhere around 1400 across the Indian grid. So, once these all PMUs are in place and along with the required communication setup, then these measurements, real-time measurements, and which are synchronized also, they will be sent to a control center where the system operator can take a informed decision and can get to see the picture or the real-time monitoring picture of the power system. So the unique feature of this VAMS, why this VAMS is so important, and why do we say that it provides a real-time snapshot of a power system? The major difference between SCADA and VAMS technology is the refreshing rate of the measurements. Now if we see the earlier scenario where we had SCADA system in place and where the information was sent to a control center via way of RTUs, there the refresh rate of measurements at the control center was as slow as once in a minute. So which means that the measurements which were captured from the various locations in a power system, they were updated at the control center after 1 minute. On the other hand, in this VAMS scenario or in this VAMS technology, this measurement refresh rate is as fast as 100 or 120 frames per second, which means this VAMS technology is capable of producing 2 measurements in one cycle of the fundamental frequency. Now we can see the difference. Had it been a SCADA system, the measurement, the system operator would have been updated by 1 minute, that what has changed in the power system. And as we know from our experience, anything can go wrong within a minute, within 60 seconds in a real power system. On the other hand, so basically I can say that a SCADA system cannot give me a real-time or near real-time information of a practical power grid. On the other hand, if we look at the VAMS system, VAMS technology, because the refresh rate is as high as, let's say, to keep it simple, 1 measurement per cycle, which means 1 cycle for a 50 Hz system corresponds to 20 milliseconds. So which means the system operator is getting updated in terms of measurements every 20 milliseconds, which is, if not real time, then I can say that it is near real time updation of the system states. So that is why this VAMS technology has been given lot of emphasis in the recent past. And because since 2003 many of the utilities have gone for it and they have deployed these PMUs across their grid, so this technology is pretty much mature at the transmission level. But what is happening at the distribution network? Let's try to see. Now if we try to see the conventional distribution system and how it looks like, so this slide explains it. Now we can see that PCC is nothing but point of common coupling. Now this point of common coupling is actually the low voltage level, or it could be our low voltage level substation as well, where rest of the network can be represented by the Thevenin equivalent of the rest of the grid. So this is our distribution level grid, and it has got very peculiar characteristics. Conventional distribution system we are first talking about. So if you try to look at the conventional distribution network, it has got some key characteristics. For example, because in conventional power system most of the generation was sitting miles away or kilometers away. For example, most of the hydro potential would be in the let's say northern part or eastern part of India, if we talk about in Indian grid context, and thermal based also it's a kind of area confined to particular area, and these distribution network would be very far off. So generation was sitting at one place, whereas loads are concentrated at different geographical place. So most of these power flows were unidirectional in nature. Unidirectional means from the generation to the load end. So it was a one-way flow of power from the generation to the load. Second key feature of the conventional distribution network has been that it is mostly radial in nature. As we can see from PCC point onwards, we have many feeders emanating out, and they are mostly radial in nature, or at best they could be very weakly meshed in nature. But we don't see very strong meshed kind of structure as we do see at distribution level networks. Third and important characteristic here is that we usually designate these conventional distribution network as the passive networks. Why passive? Because we do not have any active source of generation embedded at the distribution level. So, all in all, we can say that the conventional distribution networks are radial in nature, they have a unidirectional power flow, and they are passive in nature. Now, this is how the present day distribution network looks like. Now, with so much, I would say, advancement in the recent past in power electronics converters, and so much, I would say, favorable policies for deployment of renewable or use of renewable energy sources, now we are having various renewable energy sources getting interfaced with the power grid at distribution level, be it low voltage level or medium voltage level. So, we can see that now PV, solar based generation or wind generation, storage, battery storage, they are all getting interfaced at the distribution level networks, where still the remaining network or remaining grid can be shown as a Thevenin equivalent, but at the PCC these new devices or sources of small sources of generation are getting interfaced. Now, this breaker, the circuit breaker, plays a very important role here. When it's green, which means it's connected, so this topology is known as grid connected mode. And when this circuit breaker is off or it is opened, we call it as a standalone microgrid. Microgrid, why microgrid? Because now it's not a very large scale grid which has resulted. Now it's basically you have a small grid which is spanned over a small geographical area, which has got some load as well as which has got some generation, local generation, and this generation is able to meet the demand fully or partially. So, that is why we name this small confined area as microgrid. And although the things look very simple, but they are not a plug and play kind of devices that you just bring a PV panel and you put it into your grid and it will start working. For example, if you just look at this PV panel structure, what goes behind the scene is something like this. This is a simple single line diagram of a PV system where you have this array of PV cells and it has got irradiation and temperature, etc. And then since the output voltage is small, just to enhance it or increase it, we have a DC to DC boost converter. And since the output is DC and it has to be finally interfaced with the main grid which operates on AC system, so we have DC to AC conversion as well. Apart from that, you have this MPPT controller also to track the maximum power point. So, this is all the things which are actually embedded in a PV based renewable energy source. Now, on one hand side, although these usage of renewable energy sources has contributed in many ways, it has helped in many ways. It has helped in, let's say, reducing the transmission losses which otherwise would have occurred if the generation would have been placed at one location and loads concentrated at other location. It has also given, I would say, rise to reduction in CO2 emission. But on other side, it has also led to some technical challenges. For example, we know from our basics that if we use these kind of conversion devices, rectifier or inverters, etc., then they will distort the waveforms, which means they will reduce the power quality. Other way is that because these PV panels, they do not have inertia in them, and we know that inertia is very much required for maintaining the stability of a power system. So, these are some of the challenges, and with these emerging trends in distribution networks, now we can say that these emerging distribution networks have also got some peculiar characteristics. So, with the integration of these renewable energy sources at the low voltage or medium voltage levels at the distribution network, now we have what is known as active distribution networks, ADNs. Now, these ADNs also have some key characteristics. For example, because now conventional generations are sitting at one place, which could be geographically very far apart, and we also have local generations, small generations. So, that is why these networks, conventional distribution networks, are now called as active distribution networks. Secondly, one way power is flowing from the conventional sources, and also now they are being contributed locally by these renewable energy sources. Therefore, in conventional there was just a unidirectional power flow, but in the emerging ADNs, active distribution networks, now bidirectional power flow is also possible. Third key characteristic is that because very heavily these power electronic based converters are getting used to interface these renewable energy sources with the main grid, the power quality has gone down, which means the voltage or current signals are getting highly distorted. Another key feature which is coming up because of the interfacing of these renewable energy sources into the grid is demand side participation, which was earlier not available. Why? Because conventionally the sources of generation were just at one place and consumer had no other option but to have it or to purchase it. But now since many generators are there locally as well, which are generating power, so they can actively participate in demand response. So this is a very key feature which is coming up. Next is that earlier, because demand response management was not in place, so the loads were also not controllable. But now in ADNs, emerging active distribution networks, now we have the controllable loads into the system. Now, as we can see, many things are happening at the distribution level grid, which is making the distribution network more complicated and more dynamic in nature. How dynamic? Because the nature of the output of the generated power by these renewable energy sources is highly intermittent in nature, because they depend upon the, let's say, availability of sun, or they are depending upon the availability of wind, etc. So we get to see many new dynamics coming into picture, as well as the complexity at the distribution network is also increasing. All these things are demanding for a better monitoring or real-time monitoring system at distribution level as well. So to this end, we have done some analysis at our distribution level signals. Now for that purpose, we have made use of a Wamster PMU, which is a handheld PMU which is being installed at 11 kV by 440 kV substation at IIT Ropar. Now what we did, we captured lot of data from that PMU, and then we tried to calculate the what is known as probability distribution curve. Now if we see that frequency is actually following a bell-like curve, where mean exists approximately at 50 Hz, which is our nominal grid frequency, and mean and the standard deviation is found to be about 0.0306. So which means the maximum frequency obtained and the minimum frequency obtained from this analysis, which we got from the distribution level PMU, was 50.00 or 50.01 to 49.93. So usually the frequency was varying in this band only, and if we consider plus minus 1 standard deviation, then 60% of the variation in the frequencies were captured. So the conclusion could be that frequency at the distribution level network never remains constant, and we are bound to have the off nominal frequency cases. Next was the noise and harmonic analysis. Because that Wamster PMU, it operates at a sampling frequency of 3.2 kHz, which corresponds to about 64 samples if we take 50 hertz as the base frequency. So we calculated the power spectral density by using this formula where n corresponds to 64 points. As you can see in this graph, so a power frequency which is our 50 hertz of 0 dB appears exactly at 50 hertz. Whereas if you analyze the other variations, then the magnitude of another frequencies, they were around minus 40 to minus 60 dB band, which shows that this is the most frequently, I would say, appearing noise level in the signal. So apart from that, based on some other characteristic analysis of distribution level signals, we could summarize following key characteristic. One was that, of course, frequency at the distribution level voltages or currents, it is barely constant. It is always fluctuating within certain band of range. And next is, we have to consider noises when we are modeling the signal. And 60 dB noise is considered to be a good approximation when we want to model the noise in the signal. Next was that we have to consider the harmonics which might be present in the signal at a distribution level. Then next is, because most of the substations, they are not very far off distance wise, they are very in near proximity. This leads to a very small variation in the voltage magnitude. If you try to monitor the voltage at, let's say, substation A, and then if you try to monitor the voltage at substation V at distribution level, there won't be much difference. Same will be the case in power flows. Therefore, if you want to accurately measure them, the resolution should be very high, which means the measuring device for distribution level should be very accurate. Next is that it should have a very high response time. Why? Because now, because of the intermittent nature of these renewable energy sources, this system has got faster dynamics involved, which should be captured at a very faster rate. So therefore, these new measuring devices are expected to have a very less response time, very quick responsiveness. And last but not the least, these devices are also expected to have a good PQ detection capability. Now these are the key characteristics which we are kind of seeing at emerging ADNs. And once these kind of devices, which are the counterpart of transmission level PMUs, are developed for distribution level as well, which are popularly known as DPMUs, distribution level PMUs, or micro PMUs, then because of the huge amount of data which they are capable of generating, as I said earlier, that they are able to generate one phasor measurement per cycle per 20 millisecond, then we are expecting to have a huge amount of data available at the control center. Now just data is not enough. Once they are kind of clubbed with proper big data analytics, then they will be solving many of the monitoring, protection and control level challenges which at present the ADNs are facing. For example, the state estimation. As we know that the distribution state estimation is very difficult task, mainly because one, the system is unbalanced at distribution level. We do not have a balanced perfectly three-phase system. Second is very less amount of real-time measurements are available at distribution level, which kind of hinders the successful execution of ADN level state estimation. Next is protection. Because of the combination or interjection of these renewable energy sources, now the protection is becoming a major issue. Reason being that, as we know, this microgrid can operate either in grid connected mode or in the islanded mode. In both of the cases, in one case, the huge amount of inertia will be available with the system as a whole in grid connected mode. And in that case, the fault level contribution of individual generator will be different. And in case of islanded scenario, when you only have the renewable energy sources in the system, again the fault contribution by different DGs will be very less. And as we know, most of the protections are differential current based protection schemes. So they need to be adaptively changed, because otherwise there will be failures. Similarly, there needs to be there is a need to develop adaptive control algorithms as well. So, to summarize it, we can say that in the wake of these new RES getting interfaced at the distribution level, now the distribution systems are getting changed to what is now known as active distribution networks, and which is more complex in nature and highly dynamic in nature. And this requires a real-time monitoring in ADNs as well. And this in turn requires the development of fast and accurate monitoring devices specifically for these ADNs. Once the huge data is obtained from these sensors, then that can be utilized for various type of monitoring, protection and control applications. Thank you.